Let's study about electric flux. About electric flux, we can write that a group of electric line of forces passing through a given surface is called electric flux. And you can also write down that it is denoted by phi. Phi is the symbol we use for notation of electric flux. Another important fact about electric flux is, as we already discussed, that it is just a group of electric line of forces. Important thing is measurement of electric flux. Let's see how electric flux is measured. For electric flux, we can see it is measured in terms of electric field strength in the region. And for electric field strength, we can write that in a region at a point, electric field strength is defined as electric flux passing through a unit normal area at that point. Just be careful that electric field strength is defined as electric flux passing through a unit normal area at that point in that region, obviously. Here we can write that if phi is the flux passing through a normal area S. Here you can see if there is a surface area which is S and it is placed normal to the electric field lines, and here we can see the total electric flux which is passing through this normal area is phi. Then here we can write that electric field strength in the region we can write down as phi by S. And using this expression we can easily calculate the magnitude of electric flux. If we are aware about the electric field, flux can be written as ES. So the unit of electric field we know it is volt per meter, and area is measured in meter square. So the unit for electric flux can be written as voltmeter. Let's continue the same on the next sheet. Now in continuation, let's have a look on a situation when the area is not normal to the electric field. Here you can see that the area is inclined to the direction normal to electric field at an angle theta, as we can see here. So the electric line of forces which are passing through this given area, say this electric flux is phi, then we can resolve the area in two components. One is the component of area that is as cos theta, which is perpendicular to electric field, and other is as sin theta, which is parallel to electric field. Here if you just analyze it carefully, we can write that flux passing through as sin theta is this flux which is parallel to the area to the electric field. The flux through the area which is parallel to electric field, it can be written as 0 because we can see here no line is passing through S sin theta. And if we calculate the flux passing through S cos theta, which is the component of area which is perpendicular to the electric field, this can be written as say phi. Then here this phi can be written as Es cos theta because the normal area is S cos theta and the electric field in magnitude can be written as phi by S cos theta. So this will give us the value of the total flux passing through this given area. S will be Es cos theta. And in this situation vectorially also we can write this flux as E dot S. this can be written because here you can see if this is the area and this is the direction of electric field, and the normal to the area is in this direction, which is the direction of S vector. So here if this angle is theta, this angle must also be theta, and theta is the angle between area vector and electric field vector. So the flux coming out from the face can be written as E dot S. So always remember this expression. On the next sheet in continuation we'll also study about positive and negative flux. As just now we have seen that the electric flux through a given area can be written as E dot S, and is corresponding to a situation when we have seen that electric field exists in this direction and a given area is placed at some angle in such a way that its area vector is placed at an angle theta to the direction of electric field. Now for the same surface, if we consider its area through which electric lines are getting into it, say it is a surface which is in exactly the opposite direction from this surface, or the surface into which the electric lines are entering into, as this is the vector of the surface from which the electric lines are coming out. I'll redraw the picture for the clarity. Here you can see if from the surface area electric lines are getting into this surface and coming out from the surface, and for this surface area vector is taken in this direction, for this surface area vector is taken in this direction. So for this surface the angle theta is an acute angle, and for this surface angle theta between electric field and the surface area vector is an obtuse angle. So here we can write phi is equals to, if I take the area vector from which flux is coming out, so it will be Es cos theta, which is positive, or it can be written as flux coming out of the surface. And if I take the area vector which is opposite to this, or the surface into which the flux is getting in, the flux must be written as Es cos of this theta. So here it will be minus Es cos theta, because here the angle will be obtuse, and if this is theta, this will be phi minus theta. So this will be a negative quantity, and here it can be written as flux going into the surface. So always remember, whenever flux is going into a surface, the flux is taken negative, and whenever flux is coming out of the surface, it is taken positive. And like if we talk about the total flux passing through any surface, we can use the normal component of the area. Like for example, here we talk if this is a uniform electric field in which electric lines are equidistant and parallel to each other. If there is a disk placed in the path of electric field which is of radius r, and we wish to calculate the total flux passing through the disk, this can be written as Es, and the total area can be written as E pi r square, because the disk is placed normal to the direction of electric field. Similarly, if in another example we are given a three-dimensional sphere which is of radius r, and it is placed in the path of an electric field, a uniform electric field, then in this situation also, if the electric field is uniform, which is same as that of the previous case, and we are required to find the total flux passing through the sphere, then here we can see that the flux is getting into the sphere from one side and coming out from the other side, but the total projected area of the sphere through which the electric flux is passing is a circular area which is of area pi r square. So in this situation, if we wish to find out the total flux passing through the sphere, will be exactly the same which is passing through the circular projected area of the sphere, which is normal to the direction of electric field. So here again we can write flux is equals to E multiplied by the normal area, which is E pi r square. So it will be exactly the same, which is that passing through a normally placed disk of radius r. So in any such cases, you can easily find out the normal projected area of the body through which we are required to find the total flux passing through.